Hi, I hope I'm audible. I just checked the mail. Hi, hello everyone. So welcome to the live problem solving session for the nanomaterial and their properties course on NPTEL. Um, so just a little something about me. Manjeet Kodara. I'm a PhD student at UQ IITD Joint Research Academy, and my field of research is mostly on metal organic frameworks for electrocatalytic applications and first principle simulation using density function theory. Metal organic frameworks or MOFs are like a class of materials which are made of organic linkers, long organic linkers, and metal nodes. They provide very high surface area for reactions to take place. Yeah, so that's my research field. At the end of the session, like toward the end, I can also share some of my research with you guys, but that will be maybe in the revision session or like very end of the sessions. Like, uh, yeah. Uh, so about these live problem solving sessions, there are two sessions every week. One is conducted by me and another by Stark. The other one is at Saturday 3 to 5. I think he has already taken one session last uh, Saturday. So most of the time, like we should cover the same thing. So problem solving session is supposed to have like content would be briefly recap the topics covered in the video lecture. So that would be common. A few practice questions. Those might be different from both TAs because we are not coordinating with each other about the questions we are preparing. We're just preparing them on our own. But more or less, yeah, theme should be same. And then we'll discuss the uh, previous week's assignment. So that's after the assignment has passed its submission date. Then only we are allowed to discuss it. And finally, at the end, if you guys have any doubt, we can discuss amongst ourselves. So usually the sessions don't last the entire 2 hours. Like all the discussions and everything is usually completed within an hour or so. Uh, so or 1.5 hours. So we have plenty of time for discussions if you guys have any questions. Yeah. So this will be the schedule. So there will be 12 sessions and 12 total sessions each week. And these are the lectures which will be covered. And finally, at the end, if time permits, and we can have a revision session which will I'll go over all the basics, like briefly go over all the things taught in the course and like the common problems. Okay, so every day it will be on Monday. If there is any change, like if I have to postpone any session, I'll update you guys a week before or at least during a few days before the session. Ideally, mostly I update it at least a week before. So tentatively right now, the next session is on 4th August. Okay. Mm, yeah. Sorry. Okay. So a few important links. These weekly live problem solving sessions, they'll all have the same link, the one which I shared. And I think they share it every week again. So, problem with this one. The YouTube link, these sessions will also be recorded. So we are recording the session right now, and they'll be uploaded to YouTube. So if you miss the session, you can attend it. You can just see the video later on in your time. And finally, these slides will also be uploaded on Google Link. I'll update the link after the session wherever I upload. That link will stay consistent for the rest of the course. Okay, so yeah, these are the three important links. Now we can start a bit on the theory. So what is nanomaterials or what are nanomaterials? So anything which usually nanomaterials are classified and the size, at least one dimension lies between 1 nanometer, 1 to 100 nanometer. So anything above 100 nanometer, you usually they go into micron size, micrometer size particles. So yeah, nano object material with one or two or three external dimensions in nanoscale. At least one has to be in the nanoscale. So for so if one dimension is below like 100 nanometer, we call that 2D one, one dimension. If one dimension is below 100 nanometer, we call that 2D material. So one dimension, this can be example of a thin film or like a graphene sheet, right? Uh, so this, okay, suppose this is your sheet. This X direction, Y direction, maybe few uh, millimeter or perhaps microns, but the thickness is in nanometer. So maybe this is 10 nanometer thick film. So this is so when one dimension is below 100 nanometer, we're calling it 2D nanomaterial. And similarly, if two dimensions are below 100 nanometer, then we call it 1D material. So two dimension here would be like in case of a rod, like a nanorod. So its length may be 100 micrometers, but the diameter would be would satisfy this condition of being less than 100 nanometers. So maybe it's 50 nanometers of diameter. 50 nanometer. So this would be a 1D example of a 1D nanomaterial. They can have different cross section like hexagonal, like the material, the particle I grow have hexagonal rod shaped nanorods. And examples would be like even the carbon nanotubes, which are hollow. Again, they are example of 1D nanomaterials. Uh, Finally, when all three dimensions are less than 100 nanometer, we call that as 0D. So this example of this would be quantum dots. You have small particles where radius is less than 100 nanometers, maybe 20 nanometers, so this would be a nanoparticle of zero dimension. Again, they can have variety of shapes. They can be flakes, small flakes, or I've seen like what they call it, dodecahedron shape, those kind of particles. So yeah, for 0D, uh, all the dimensions are below, all three dimensions are below. Or if you want to remember it, you can remember it other way. For 0D, uh, none of the dimension is uh, above 100 nanometers. For 1D, one dimension is above 100 nanometers. For 2D, two dimensions are above 100 nanometers, right? Because we live in a 3D world, so we subtract the other one and we can, if it's easier to remember. And nano objects, nanoparticles, yeah, they can be nanoplates, fibers, nanotubes, nanorods, nanowire, quantum dots. So, so there are also three-dimensional nanomaterial, which are a bit different. They are materials composed of, they are 3D materials which are composed of nanomaterial. So, for example, if you stack these layers of graphene onto each other, so but if they form a single crystal, then it's not a nanomaterial. But if you suppose you have graphene in one orientation, say we call it A, and then there's another graphene on top, which has different orientation. And if you Google it, you'll find like graphene can have different orientations. So this you call B. Now A, B is different. Now you have another one C, which can be either A, B, that can be A or different C, and you stack multiple of these layers on each other. Like you'll get a cube with something like this. Okay. So here, since each of the layer is made up of nanomaterials, nano sheet, nano plate, whatever you can call it, uh, that's why we still call it nanomaterial. So this is example of a 3D nanomaterial where you are using some either of these 2D, 1D or 0D nanomaterials to get 3D structure. You can have the a metal block of metal where the grain size is uh, nanometer range. So if you know metallurgy, all everything is like how do you say it? So metal iron. So iron has FCC structure, can have FCC or BCC structure, right? So these are the crystal structures, how the atoms align. Now, like this is FCC. Maybe I will go in the next page. Suppose you have FCC. Uh, FCC is face-centered cubic. You can read upon it, read about it later. No need to remember right now. So this is suppose FCC, and now you have more atoms which are arranged in the same way, like this way, and this corresponds to this one, this corresponds to this one. You have two unit cells now. Similarly, if you keep on adding, you'll get some material. So it'll it will be cube of some size, right? In this case, at least, depending on surface energy, it can be different shape. But suppose this is a cube, okay, and all of them they don't have any defects, so all the bonds are complete and there's no grain boundary. So this is a we call this as one grain. So and now you have different grains which combine to form your material. So if you have a so here you can define a direction of this crystal. Suppose you can have grains. So this maybe this direction I'm talking about. This direction is x. So wherever uh, the space centered, the edge of the space, I'm calling this as x. So suppose I have this big chunk of material and I have this small section there, random size. Okay. So in this one, if you're seeing this face centered uh, on top, they may be aligned in this way. This one, they may be slightly aligned in this way. This one may be again offset by some other direction. So if you see this direction, x, so in this grain, the x direction is this way, and you rotate it a bit, and you get this grain. Similarly, if you have this grain, the direction may be slightly different. So these are crystal directions. So different grains have different crystal orientation. We call this crystal orientation. And in between these two, we have a grain boundary. So if you see at the grain boundary, you will see a mismatch of atoms. So this crystal is pointing in this way and this one is pointing other way. There will be atoms in between in this layer, which will be confused. Should they be aligned to this way or this way? So some of them would be aligned this way, some this way, and some would get confused and would be aligned to neither of these. So yeah, so where are we? Yeah. So these, if the size of these grains is less than 100 nanometers, so they can be spherical grains and they're less than 100 nanometers, and you're forming a bulk with these grains. And this again would be a category of 3D nanomaterials. Okay, so the example would be like iron, if you're a steel or iron or titanium, any metal, and you cool it in such a way so, so that the grains do not grow as big and remain small size, and we'll get a 3D nanomaterial. Okay. Some examples of nanomaterials. So here you see colors due to different effects. So here also you have gold particles, but it's just their size is different. Again, they are in nanometer range. If you have big like millimeter size gold particle, it'll probably settle down. If you go a little bit higher, in the lower size, maybe 1 micrometer, that again is not in nano range. So what will happen? You'll find make a colloidal solution of gold. So it will still appear gold, like it may not have the shine of a gold, but it will be brownish color solution. But if you go even lower size, then you start seeing the color changes of the solution. The solution, the color of the solution changes. So here the reason is surface plasmon. So way the light interacts with the surface plasmons on the gold particles, that changes the color of these solutions. So the smaller the radius, the plasmons behave differently, interact with the light differently, and you get different colors. So here's surface plasmon is the reason for this color. Okay. Here you have uh, cadmium selenide quantum dots. So CDSE is a like, uh, semiconducting material which has some band gap. This band gap depends on the size of these particles. Okay, so if you we'll cover this later on. All these things will be covered later on. So this is just introductory. So I'm just showing you how the different nanomaterials are. So if you have bulk CDSE, cadmium sulfide selenide, it will have particular band gap, right? Since it's a semiconducting material. This is your valence band, this is your collection band. However, if you go down to nano range, so if you start decreasing the size of the particle, if D decreases, this band gap W, this will start increasing. And that will change the how which light it absorbs, and it uh, that absorption would lead to again the other colors would be scattered. Due to absorption, you'll see different colors. So in this case, it's due to changing band gap. The color here you see is due to changing band gap of the material since we are going into nanometer range. And then third example of a color, here you see different colors in a peacock feather, right? So here your different colors you're seeing is due to nanostructures form on the surface. So maybe there would be some kind of ridges, and these dimensions would be less than 100 nanometer, maybe 10 nanometer, 20 nanometer, something like that. So these nanoscale ridges or features, they scatter the light different in a different way depending on the size of these features, and that scattering gives you different colors. So there is no change in band gap or surface plasma effect. It's just due to yeah, the surface features, how they scatter the light. Again, if you go in uh, nanoscale, you'll see different colors for different length scales. Okay, surface area to volume. Okay, so this is the most important feature of nanomaterials. What happens is if you have a bulk material, so some radius r, will have this volume 4 by 3 pi r cube, and the surface area would be this, right? 4 pi r square. If you calculate the surface to volume ratio, just divide the volume divided by the surface area. I think it's reverse here, right? It should be surface area is 4 pi r square divided by 4 by 3 pi r cubed. 4 cancel, pi cancel, so you get uh, 3 by r, I think. Yeah, that should be good. This is incorrect. This is the 3 by r, and yeah, this is also going incorrect. So 3 by r. So now you can see how this ratio of surface area and volume depends on the radius. So if the radius is decreasing, so if the radius decreases this way, so this is volume fraction of surface atoms. Uh, volume fraction of surface atoms. This volume fraction increases. So in this way, you can Like here, if you're reducing the particle size, if R is decreasing, S over V ratio is increasing, right? They're inversely proportional. Your surface area is increasing uh, increasing faster. So yeah, compared to the volume, the surface area is increasing faster, so you get more surface to volume ratio. So that means more of the atoms are sitting on the surface. So that's what volume fraction of the surface atoms. So volume fraction is just how many volume of atoms on the surface divided by volume of atoms on in bulk. Bulk is anything below the surface. So if you have a nanoparticle like say a nanoparticle, so you have atoms sitting on the surface, right? And then these are bulk. Anything within this one, these are all are your bulk atoms, and these are all this first layer is called, we are calling this as the surface layer of atoms. Just calculate the volume of this and this. So as you decrease the radius, you see that the volume fraction increases exponentially as you go down the radius size. If you go to like very small sizes, like you have only few atoms. Now so this is a nanoparticle. Now all the atoms are sitting on the surface, so your volume fraction would become 1 at that particular radius. This would depend on the radius of the element and whatnot. Mm, yeah, so here I calculate the derivation. So yeah, so we're assuming volume bulk as the volume of the entire particle. So if you have r radius particle, the volume would be 4 by 3 pi r cubed, right? If you want to calculate the surface volume of the surface atoms, you assume there's a thin shell of atoms on that sits on the surface. This shell is just single atom thick, right? And you assume its thickness is T, right? Now, uh, if you calculate the area, the volume of this would be R, so 4 by 3 pi R cubed minus, so this complete is R, and this inner one, the radius till the inner one is R minus T is the thickness of the shell, so you get 4 by 3 pi R minus T whole cubed. So that's what you get here. Now if you expand this term, uh, yeah, I took the 4 by 3 common. You have r cubed minus r minus t whole cubed. If you expand this term, your r cubed would get cancelled. You're left with t square and t cubed one. So for any atom, unless you go very small, the particle size is very small, this thick The T would be still in angstroms, maybe. Like, T is a single atom thick layer, right? Thick layer. So atoms are like in angstrom or smaller in few angstrom size, right? So this thin layer T is very small. Right? So if T is much less than 1, T cubed is even lesser. T square is bit more, bigger than T cubed. But so we can ignore these two values since your T is very less than 1. So square and cube terms we can ignore. And you're just left with this minus 3r square T terms. Uh, yeah, just rewritten it here. So R square gets cancelled. You are left with only these three terms. Out of these three, these two you can ignore. You approximately 0. And you're left with only mm, this term. So this is volume of surface atoms. Volume of surface atoms. 4 pi r square T. T is your thickness of the shell. So now if you take the ratio of the, so this is Vs and Bb is volume of bulk atoms. Volume of bulk atoms is just volume of the complete particle. If you take the ratio of these two, you get 3T by R. I think, yeah, this was the derivation. I think he's shown this formula in the slide to get the derivation. So V naught, you just move it here. V naught is the volume of the entire particle, which is Vv in this case, and we get this formula. Now, if you see, we get this formula, and if you reduce the particle size R, P is more or less fixed since there's a thickness of a single layer of atoms, right? Thickness remains fixed. V naught is initial volume, A is surface area. I think just if you look at this one, yeah, this one. So VB by V naught is 3T by R. T is constant, T is more or less constant, so it's just inversely proportional to R, so you get exponential relationship. Okay, and this is how you get this plot. Okay. This again is just example of bulk material. So this is bulk. We have one dimension, this dimension, which is less than 1 millimeter. We have thin film, we have 2D material. And then where your two dimensions would be less than 100 nanometer. This is greater than 100 nanometer, so this is your 1D material. And quantum dots, all three dimensions, if they are less than 100 nanometers, you get 0D or quantum dots. Okay. So this is how uh, the density of states changes. So I told you about the band gap. uh, So density of states is available energy levels available for the energy levels an electron can have in a material. And how many at particular energy level, how many sites are there? That's what you call density of states. So for bulk density of states, you have a continuous density of states. So at any electrons can occupy any energy level between this in between their band gap. Not in the band gap, sorry, in any of the bands. It can have any energy levels. If you go down to thin film, that is 2D, your density of states becomes this staircase like stuff. However, still, if you connect the bottom of these staircases, you'll still get this parabola. So that is in most simplest models, the density of states, the E versus K plot, this is GK. EK plot is parabola. Okay. So you still get this parabola, zigzag which touches the parabola. If you go down to 1D material, nanomaterial, now 1D nanomaterial, now you get even more discretization of the density of states, and now electrons cannot occupy all the energy levels. There are some gaps where which electron can energy cannot the electron cannot be stored in atoms. Yes. And but still there's some thickness of these bands, right? You have either these energy levels or these energy levels or these energy levels. Or if you go down to quantum dot or one zero D material, these energy levels become completely discrete, and the electron can only possess certain uh, energy levels. So that would depend on this and so air A is their size, the nanomaterial, and is just mass of electron. I think that is like Planck's constant. So depending on the different ends, you'll have different energy levels. In this amount. Okay. Now, check. So we finished the assignment. Okay. So week one assignment is due on 6th. So um, okay. So next Monday still. Oh, you're both assignment one and two are due on 6th. 6th. Okay, then I'll discuss the week assignment. 11th then. I'll list of both the week one and week two assignment. And today you can see, have a look at some yeah, self-assessment questions and maybe the week zero assignment as well. So some self-assessment questions. Define nanomaterials. So materials with at least one dimension below 100 nanometer, we call them nanomaterial. 1 micron is 100 nanometers. So just the length scales this you have meters and you have millimeters, which is 10 to the power 3 meter, minus 3 meters. And you have your micrometer, the 10 to the power minus 6 meters. Nanometer, that is 10 to the power minus 9 meter. Nothing yet. Picometer, picometer, which is 10 to the power minus 12. mm, 10 to the power minus 12. I think femto is 10 to the power minus 15. On the side, a kilometer, 3 mega, megameter. These are usually capital and these are picometer, PM, centimeter. Give example of 1D, 2D, 3D nanostructure material. So 1D, again, like I said, at least two of the dimension will be less than 100 nanometer or in nanometer range. And the third one is greater than 100 nanometer. So you have rods or tubes or wires, all the anything. These two, and the radius, these two dimensions. Third one is along Z. So X and Y are less than 11. Two of the dimensions are greater than 100 nanometer. You get nanosheets of graphene. You know structure of graphene. You have hexagonal uh, atoms forming hexagonal lattice. So this is your, if it's just one layer, even if you can have multiple, maybe few layers, one or two layers, still the thickness would be less than 100 nanometers. So it will be nanomaterial. And obviously, these two dimensions can be yeah, has to be bigger than 100 nanometer for it to be a 2D material. Finally, 3D is again, as I said, nanocomposites, where you can use. So if you have a bulk sample and you embed nano, so suppose nano wires in the this sample. If you have some steel which has titanium or maybe tungsten nanowires. So again, this is a nanomaterial, 3D composite nanomaterial. So you have these wires inside it. Maybe they are giving some strength, providing hardness or wear resistance or whatever. Okay, this is a composite material. In lecture 2, we have question. Give example of natural and man-made nanomaterial. So for nano, you can see like these tails of these, what are they called? Like so how they move, their nanomaterial, the wings of butterflies. So in nature, blue color doesn't occur very commonly, blue or white color. So mostly whenever that happens, it's due to some nanostructure materials. So this butterfly would have, is it, I don't know if they're explaining the gecko or butterfly, but yeah, there would be some nanostructures which would be scattering the light, blue light, and you are getting this blue color. I think these are nanostructures. And yeah, I think this is this one. We have nanostructures like this X things which scatter the light, um, yeah, giving a blue appearance. Gecko feet, geckos, there's a slightly different species compared to your house lizard, but even they have very sticky feet. So geckos are even more special. They can even stick to glass. I don't think our household lizards can walk on glass. But, yeah, these geckos they can. They have like tiny hair-like fibers on their feet, which again interacts the underwater forces between the glass and the surface, and they stick to. They can walk on any surface. Uh, Spider web, yeah, can be example of a natural nanomaterial. Man-made is anything like a lot of iron powder, nano, tungsten nanorods or silver nanorods. Plenty of example in chemistry. Volcanic ash can be of nanometer size. Viruses are small. Soot from combustion. So you see the PM2.5. These are less than 2.5 micrometers, but they can be even smaller. Can be less than 100 nanometers. So right now everyone is talking about these, but these still can be blocked. And like one, they're difficult to get in your blood, but still they get in your lungs and all. But these nanoparticles, you can have nano soot particles or nanoplastics. Even nowadays, people are worried about uh, finding plastics in their body. So even newborn babies have plastics in their bodies, so they get it from their mother. So these, when they're in nanometer sizes, they all our tissues which block these foreign particles, even they cannot uh, block them. So pretty soon people will be worried more about the nano particles. Hence we have figured out how to get rid of these PM 2.5. People would next focus on nanoparticles in their environment. How gecko can stick to the walls and ceiling. So there are thousands of tiny hair-like structures at the bottom of the lizard store. And these At the end, they have even more smaller hair-like structures which branch out and they provide like very high surface area. And it's a strong mineral wall spores to stick to the tiny surface. It's like just assignment, I don't know, accidentally cover on questions. Right. So, some practice questions. Size of nanomaterial lies between. I should probably with them as slideshow appear makes the question like a solution appears after some time. Yeah, it's visible already. Okay, any if the particle size is between 1 to 100 nanometers, we call it nanomaterial. Fullerenes or buckyballs. So if you use C60, there are uh, carbon nanoparticles, which are typically made of 60 carbons. So they can have even higher C80, I think, or C70. And they can have more or less than that too. C60. Yeah, this is example. So buckyball is kind of like a football. Yeah. Yes, C60. So that's again, what will be the size of the ring? Mm, Down. Oh, very small, like point 0.7, you know, like, or yeah, the electron cloud is these uh, carbon atoms are sp2 orbitalized. Will have pi orbitals of shell that would form a larger. The interaction of sphere of this will be larger. Which ratio decides the efficiency of nanomaterials? So, yeah, surface area to volume ratio as you go down, the size of nanomaterial, surface area increases a lot. So this ratio of surface area to volume is very important. You can increase the surface area just by increasing volume. So you have 1 meter cubed, 1 meter square, 1 meter cube. And here if you have 2 cross 2 is 8 meter cubed. So you have increased the surface area, but doesn't make it a nanomaterial. So for nanomaterial, we need to increase the surface area to volume ratio. That's when you see the unique properties of nanomaterial come to play when you go down the size. It's when you do the surface area to volume ratio. Okay. Which property of nanomaterial provides driving force for diffusion? So high again, high surface area to volume. So if you can imagine like it's a cube or a sphere. You have a sphere The atoms sitting on the surface are have incomplete valency, or they're not bonded as strongly as the atom sitting in the bulk. If you have an atom sitting in the bulk, that's attracted or bonded in each direction, right? And if you see the surface, atom sitting is only forming bond along the surface or within the bulk. There's no bond in this direction. So this is a high energy state. Since the bonds are incomplete. So usually these atoms would migrate inward, try to migrate inward to reduce the surface area, thus reducing the overall energy of the system. So what you have is like if you have some weird shape, this you know sphere has the least surface area to volume ratio. If you calculate the surface area to volume ratio, sphere has the least one. You can calculate this for multiple shapes. I think we'll do this in the course for rod or maybe a sheet. You calculate the surface to volume ratio. You will find is lowest for a spherical particle. So everything eventually wants to become a square to minimize atoms sitting on the surface, since all of them are high energy atoms. So if you have this random shape, eventually over time, all the steep curvatures, these would get blunted. This would become something like this, and eventually this will form a sphere of equal volume. The volume remains conserved. Surface area would decrease. Near diffusion. Yeah. Nanomaterials can be 0D. Yeah, you can have any dimensionality. 0D are your quantum dots, as we discussed. 1D are your nanowires. 2D nanosheets like graphene. 3D you have composites which consist either of these nanomaterials, quantum dots, nanomaterials. 0D, 1D, or 2D materials. Yeah. Now, even you can have nano composites as well. Like you can have a nano sheet or thin film. This may be around 50 nanometers. And inside you can have some even smaller nanowires embedded inside this sheet. So this will have different material and this will be different. There, this here, this would be a matrix. This would be a pillar or so different material. So you can have composites which are in still in nanoscale size. Okay. In the structure of fullerene, each atom forms a covalent bond with three other atoms. Yeah, I just showed the structure and copy it here again. If you take uh, this atom, it's bonded by one, two, three atoms. So it's sp2 hybridized. If you remember here, ninth, 10th. Oh, sorry. Yeah, 11th, 12th chemistry. Or can be sp3 hybridized or sp2. sp3 usually forms four. It has four bonds formed. It has tetrahedral shape, right? And sp2 usually forms. It has three bonds. 120 degree, like degree. Angle is 109. Okay. So here is sp2 sp3 hybridized. All the bonds are completed. So no, no, no. I was just saying, like, if you see these angles, this would be less than 120 degrees. Is they are kind of curving inside. I don't know if that stabilizes or destabilizes these bonds. Increases this. I think it should decrease the structure energy, but yeah, I don't know. I don't know. A material with one dimension in nano range, another two dimension bigger than nano range, obviously. Dimensions are large is called, yeah. So one dimension in nano range, which is it. Film. So these two dimensions, this and this one, greater than 100 millimeters. X and Y. Its thickness is less than 100 millimeters, less than 100 millimeters. So we have a 2D nano sheet. On both sides of a CNT, which carbon structure is placed? The first images. So CNT, as you know, is just a graphene sheet rolled onto itself. And so the way you roll this graphene sheet can have different parallelities of these nanotubes. But to make the ends so that the ends are stable, you'll have hemispheres, uh, hemispheres, yeah, carbon atoms. There will be C60 hemispheres. The size would depend from maybe this is C60, this would be C80 or something, C80 or C90. There may be quantum dots are used in they're used a lot in solar cells, LEDs. If you are aware of the newer display technology, you see advertisements of quantum dot based displays. You can have sensors. You can have quantum dots which deliver drugs to specific target sites, like specific cells in your body. What is a graphene? So graphene is just a single layer of graphite atoms. Single layer, right? Um, and here each carbon is bonded to three other carbons. By sp yeah, sp2 bonded. Okay. This I think I'll discuss in next class. That's more or less what I wanted to cover in this session. There is zeroth assignment. Yeah, zeroth assignment in this case. Week zero. Oh, what is the prefix nano mean? Or if you just Google it, nano means dwarf. Also means 1 millionth of something. So yeah, kilo is 23, gram beta, kilo smaller, milli, micro, so nano is the prefix representing 10 to the power minus 10 magnitude and derived from Greek word nanos, which means dwarf. In scientific terms, nano refers to 1 millionth of power silicon. What are called nanomaterials? So materials with at least one of the dimension which lies in your 0 to 100 nanometer, called them nanomaterials. They can be composites as well. Uh, of the bulk, maybe all the dimensions are not less than a nanometer, but they may have composites inside. Okay. What is the usual shape of nanomaterial? They can have any shape actually. If you go down to small nano quantum dots or 0D nanomaterial, they can be spherical, they can be, I saw that football shaped buckyball, they can be hexagonal flakes, so they'll be very thin hexagonal flakes. I've seen some nano leaves, so these if particles they form like a leaf kind of structure. And yeah, any shape you can imagine they can take in nano scale. Sheet, you can have flake. Sheet and flake usually just refer to something. If something is large, the other two dimensions are fairly large. Maybe these are 1 millimeter. So you call this a sheet. And if the same thing, then maybe in 1 microns. Mm, yeah, like it can be micron or even nanometers. Sometimes people also call micron region the follow the fluid. It's just the aspect ratio is it appears more like a thin flat disk. Disk. However, if all the three dimensions are still nanometers, sorry, suppose you have this hexagonal particle. Still, this is maybe 10 nanometers, but its thickness is maybe even lesser, like zero point 0.1 nanometer. So you'll call this as a flake instead of sheet. They're regular, they can have regular shapes. Yeah, and like sheets can be of regular shape. Particles can be of a regular shape. Tube, dodecahedron, and geometric structures. Yeah. What are the three criteria for defining nanomaterial? The size of a nanomaterial. Okay, yeah. Its size dimension should lie in less than 100 nanometers, and its surface to volume ratio is like very high. Mass increase volume. Why are nanomaterials so reactive? Again, this is due to surface area to volume ratio. So as you saw, if you have a particle, the atom sitting on the surface have incomplete bonding, so they want to form bonds with other things. They want to react. Uh, so yeah, they want to react, so they are reacting. And this is an interesting case of metal nanoparticles. I used to work in Hilti, so there I had a room filled with metal nanoparticles. So the particle size would be nanometer range. That room was a fire hazard. If you ever get some nano metal powders, do not throw them in air or expose them to air all of a sudden. What will happen is, since most of the atoms are sitting on the surface, so suppose if you have iron nanoparticles, iron rusts. If you have bulk, just the surface would react with the oxygen, and bulk is more or less just iron. But however, on the surface, you'll get a three, two. But if you go in nanometer range, what will happen is a lot of your almost all of your atoms are sitting on the surface, ready to react. So your reaction, some of these atoms would react, release energy, react, energy is increased, released. That will increase the temperature, it will increase the reaction rate, and that will release more energy, increase temperature. So they will form a positive feedback loop, and you will get explosive. So metal nanoparticles are explosive. So what happens when particle size is reduced to nanoscale? It changes both their physical and chemical properties due to change the surface area to volume ratio and quantum effects. So quantum effects we talked about were like changing band gap or uh, band gap becoming discrete, band structure becoming more discrete, and chemical properties would be like uh, reactivity or something like that. Physical property, the density would change. Uh, what else? Density, melting point will change. Right? Chemical properties, the reactivity, uh, how they react with different atoms will change. The electronic properties will change. The gold slab melts at 1064 degrees Celsius. Then the gold particle will melt at, so it will melt at lower temperature. Melting point of gold nanoparticle is typically lower than that of gold belt slab. This phenomenon is due to increased surface area to volume ratio of nanoparticle, which affects the thermal part. We'll go over these things in more detail as we go along the course. In case of nanomaterial, rate of chemical reaction is proportional to, so nanomaterials have very high surface area relative to their volume, which increases the number of reactive sites available for chemical reaction. proportional to a surface area to volume ratio. Bulk materials insulate and their properties irrespective of the size. True, that we consider if you consider density or the melting point, they usually remain same if you have a 1 kg iron cube or maybe 5 kg iron cube. The density and the melting point would remain same. Uniqueness of nanomaterial lies in the fact that nanomaterial form a bridge between bulk material and the atomic or molecular level. That's true. So at atomic or molecular level, atoms behave completely differently, and due to bulk, the most of their chemical heat in between those two regions, you have your bulk atoms. Mm, Yeah. Okay. So, if you guys have any doubt, you can ask me now. So, I'll upload the recording of this session on YouTube. Slides will go upload. Google Drive. I'll share the link. Update the link in the YouTube the next class. We'll make it compacted URL. And yeah, a deadline for first assignment is 6th August for 6th and second assignment. So submit it before the date. And I think the registration date is quite far away. So if you want to get certificate in the course, you can register for the exam. There's some exam fees. And that date, okay, exam date is on 26th October. And if you register and pay for 11th August, so for 11th August, you can register for the exam. So if you want to get a certification in the course, yeah, great. Okay, yeah, okay. So this is 1,000 rupees. Last date is 15th for this session. I don't know after that. Yeah, okay, how much would be the registration cost? I don't know after 11. Okay. Late fee will be applicable. Yeah, if you want to avoid late fee, register for the exam for 11. Okay, any doubts? Okay, I have some question. How will you define particle, whether grain in nanocomposite? Remember, yeah, particles with this, yeah, which If your size of the grain is less than within this 1 to 100 nanometer, then we'll pass it, call it a nanocomposite. So nanocomposite is anything uh, whenever you're using 0D, MD, or 2D material, and using these, you form 3D material. These we call as nanocomposites. So, particle, in case of grain, particle would be a single grain which has same crystal orientation. I hope that was your particle can be bigger than nanometers. No, definition of particle doesn't mean it's a nano. It's just if its diameter is less than falls between L and B. So we call it start calling it a nano particle. Okay, I think beginning classes mostly just introductory stuff. I think we can end the session.